popular amusement park ride, a rotating cylinder of radius 2 meters is set in rotation with a speed at the rim of 14 meters per second, as in the figure. The floor then drops away, leaving the riders suspended against the wall in a vertical position. What minimum coefficient of friction between a rider's clothing and the wall is needed to keep the rider from slipping? Circular motion is a force problem, and the first step in every force problem is to draw a free body diagram. This dot will represent the rider inside the cylinder. The first force acting on the rider will be m times g. The rider's mass is not specified, so we'll simply have to leave this as letters m times g. Next, we notice that the rider is in contact with the wall of the cylinder. Contact forces always include a normal force, where normal is the mathematician's word for perpendicular, and that force will be here. And they may include a frictional force. We'll stop for a moment and think about what kind of frictional force this is. Kinetic friction is the kind of force you get when two objects are sliding along one another. The strength of kinetic friction is mu subscript k times the normal force, and it is always equal to that amount. However, if two objects are not sliding, they can still experience a frictional force, and that frictional force is given by the formula F subscript s, which stands for static friction, is not equal to, but is less than or equal to, mu subscript s times the normal force. In most problems where we formulate an equation, we would never substitute for the static frictional force something that it was not equal to, but merely less than. However, in some problems, we have a condition in the wording of the problem that stipulates we shall be considering friction to have reached its extreme. This problem asks us what minimum coefficient of friction is necessary. Because we are asking for the minimum coefficient of friction, that means that the friction itself has become an extreme, and therefore we do have the special case where the static friction will be equal to mu s times the normal force. Now, the static friction is directed so as to prevent sliding. If it weren't for friction, the person would obviously slide downwards, and therefore we recognize that the static frictional force on this person will be along the surface of strength mu s times the normal force and upward. That's it. The person is experiencing gravity and the contact force in two components, normal and friction. Our two-dimensional free body diagram will receive a coordinate system, and as always, the principle by which we align the coordinate system is to be along the direction of the acceleration. Even though this person is moving with a constant speed of 14 meters per second, they are nonetheless experiencing an acceleration because they are moving in a circle, meaning that their velocity is continually changing direction, and even a directional change of velocity is an acceleration. And we recognize that the direction of the acceleration in circular motion is toward the center, and in the drawing that we've made, that would be towards the left. We will call that positive and label it with the word centripetal. To finish our coordinate system, we need the second coordinate to be perpendicular to the first, and we'll name that to be vertical. This free body diagram is nice in that all of the forces a priori are already lying along the coordinate system, and so our equations for both the centripetal direction and the vertical direction will not require us to take any components of any forces. Let's begin. Starting with the vertical direction, we notice that we didn't label the plus direction for vertical because there isn't any acceleration in that direction. We'll call upward to be plus because that seems to be most natural, and so mu s times the normal force minus mg equals mass times acceleration, no vertical acceleration. The second equation will be in the centripetal direction. As labeled in the figure, the centripetal direction is to the left, and there is one and only one force in the centripetal direction. That's the normal force N. The sum of forces is equal to m times a, and we ask ourselves the question, is there an acceleration in the centripetal direction? The answer to that question is always the same, yes. The acceleration in the centripetal direction is v squared divided by the radius of the circle that you're moving in, and that completes our second equation. These two equations have a total of 3 unknowns. We don't know the mass of the person, we don't know the normal force, and we also don't know the coefficient mu sub s of static friction. However, if we're fortunate enough, and I believe we are, we will simply proceed by attempting to eliminate one of the unknown variables. It'll be easiest to eliminate the normal force because the second equation, or centripetal equation, already says that the normal force is mv squared over r, and we can simply plug this result into the first equation, and that will yield the following. Here, for convenience sake, I've moved the mg term to the right-hand side of the equal sign, because that also allows us to see very simply what the cancellation is. The cancellation is that the mass drops out of this equation, so that rather than this being an equation in 2 unknowns, it is in fact an equation in only one unknown, that's mu s, and we can solve for mu s rather simply. Mu s is rg over the velocity squared, and plugging in the values we get the numerical result, 0.1. This is in fact a rather small coefficient of friction necessary to keep you up, but that's kind of what you want. You'd like to have more friction than necessary before you just barely slip down and fall inside this carnival device, also known as the Gravitron.